This video is about Hess's law, and what Hess's law does is give you a way to calculate what the delta H of a process is going to be, and it can be really useful when you cannot measure it directly. So using Hess's law to calculate the heats of reaction, or the delta H of a reaction, sometimes it's hard to measure delta H. For example, if something happens really slowly, too slowly to measure, or if it occurs in steps, or if it's hard to control. What Hess's law states or allows you to do is that if you add two or more thermochemical equations together to give a final equation, you can add the delta H's together also. So it's a way to use algebra and known values to calculate unknown values of delta H. So the reaction, or the process that we're going to look at first, is when two forms of carbon at 25 degrees, one is diamond, which we're all familiar with, and the other one is graphite, which is like coal, also a form of carbon. And this process, diamond turning into graphite, what is the delta H for this process? And we can't really measure it at 25 degrees because it happens over millions and millions of years, so we're unable to measure it. But it turns out we can use Hess's law to calculate it using known reactions. So graphite and diamond both can be converted to CO2. So carbon, graphite converted to CO2, this delta H can be measured, negative 393.5. Also, carbon diamond can be converted to CO2. Its delta H can be measured, negative 395.4, and these are all kilojoules. And what we can do is this conversion from diamond to graphite is this delta H here, and it turns out that we can use the known values to figure out using algebra what this little unknown value is going to be. So think of these as balanced equations, where we can write the balanced equation and determine the delta H for that equation. Graphite to CO2 and diamond to CO2, its delta H is known. And then using algebra, we can cancel out intermediates and get an overall equation. So equation A, which is the first equation up here, the graphite equation, we can reverse that equation. So we can flip it around, and if we flip it around, we have to change the sign of delta H, because if we reverse the process, the delta H number is the same and the sign is going to be the opposite. So let's do that. And this is a typo, this should be a 3 here for delta H. So we completely reverse the, so it's CO2 going to make carbon graphite. Flipping the equation around, we reverse the sign of delta H. It's exactly the same number, but now it's positive 393.5 kilojoules. The sign is reversed. So now what we can do is rewrite the equations A and B, where A has been flipped around and its sign is opposite. B equation is the same, diamond plus O2 making CO2. So its delta H is the same, and we just analyze them using algebra. So if we think of the arrow as an equal sign, CO2 on both sides of the equation can cancel. O2 is on both sides of the equation, and it can cancel. And we are left with carbon diamond goes to make carbon graphite. And whatever we do to the equation, we're also going to do to the delta H's. So it's going to be positive 393.5 plus negative 395.4, And then we add those two numbers together and we get negative 1.1 kilojoules. So it's a way for us to measure the delta H for diamond turning to graphite minus 1.9 kilojoules for a process that we can't actually do in the lab. So that's the summary. Because it is negative, it is an exothermic process, only by a little tiny bit. It's a very, very small number. So we're going to practice using Hess's law for the next few equations. First, you're given the equation that you want. This is the equation that you do not have the delta H for, but you are given the delta H for the two following equations. So as they're written now, they're not going to cancel and get you what you want, so you're going to have to do some manipulating of the equations. You might have to multiply it by a factor or flip it around, and whatever you do to the equation, you're also going to do to delta H. So for this problem, the first equation here, the PCl5 equation, we're going to flip it and multiply it by 2. So when it's flipped around, it's PCl3 plus Cl2 goes to make PCl5, and we multiplied everything by 2. When we flip it around, we change the sign from positive 87 to negative 87, and we also multiply the delta H by 2. So for this process here, the delta H is negative 174. And then to that flipped around equation, we are going to add the second equation. And the reason we flipped it and multiplied by 2 is because now PCl3 can cancel. We need to get rid of it so that we get our final equation. This is what we want. So we want everything else to cancel. 2 PCl3 is over here. 2 PCl3 is also here. They cancel out. And then the net equation is whatever doesn't cancel, whatever you have left. And then you add the delta H's together. So we add minus 174 plus negative 574, and that gives us negative 748. The other way that we can use Hess's law is to calculate the standard heats of formation using tables. So in the back of your packet, you are given 4 or 5 pages of thermodynamic data tables, and we are going to use those tables to do problems using Hess's law for what we call the delta H of the reaction. So the overall reaction, if we're talking about formation reaction, is the sum of all the products, the delta H's of all the products, and these are found from the chart, minus the sum of all the delta H's of the reactants. So for this example here, we're going to calculate the delta H of this reaction. 2CO plus O2 gives us 2CO2. So this is the product, and we're going to look up the delta H for CO2, for O2, and for CO. And what we'll find is if we have an element in its standard state, and in this case it's oxygen gas, from the chart you're going to see that the delta H's for those are all going to be 0. They're all in kilojoules, they're all from the chart, and what I did here was write the numbers above each formula. So find CO2 in the chart, and it's negative 363.5. CO is negative 110, and then O2 is 0. So again, we're going to plug these numbers in, multiply by any coefficients, and it's going to be the sum of all the products minus the sum of all the reactants. So what we get for this equation is the products, CO2 minus 363.5. The 2 here, we have to multiply this by 2 because of the 2 in the balanced equation, because of this 2 here. So it's 2 times CO2, and then minus the sum of all the reactants. And the reactants are carbon monoxide, which is 110. It is also going to be multiplied by 2 because of the 2 here. And that is going to be plus oxygen, but oxygen is 0. And so it's going to be minus 727. Because of the signs, we are subtracting a negative number here. So those are going to be added together, and that's the total is going to be negative 506 kilojoules. So on the next page, the next slide, all of the problems for the delta H have been worked out, but it'd be good if you stop the recording and try to do the work yourself, and then turn it back on and check your answers. To make it easier to check your work, the keys for all of the Hess's Law practice worksheets are all scanned and posted in Schoology.